Alrighty, welcome to this speed distance time question. We've got a speed time graph here. We're asked to work out the average speed of the vehicle during the 50 seconds. So first of all, let's just remind ourselves, average speed is actually your distance travelled divided by your time taken. So we've got the time taken, it's 50, we just need to know the distance travelled, but actually we're told that here 1.35 kilometers. So basically set for it, except the answer says give it in meters per second, so we need to convert it 1.35 kilometers into meters. We can do that by multiplying by 1,000. Really important to do that. And then we can divide by this time taken of 50. Okay, what to do now? This is a non-calculator question. We can divide top and bottom by 10, so we basically cancel those zeros off. And then I think I'm gonna just work out what 1.35 times 100 is, and that's going to be 135 divided by 5. And now I'm left with a simple division. So 5s into 1 don't go, carry the 1, 5s into 13 go twice, remainder 3, 5s into 55 go 7, 27 meters per second. Done. Work out the value of k. Alright, how are we going to do this? Well, something that's really important to know is that the area under a speed time graph is the distance travelled. So I know, I might even write that down actually, area under graph equals distance travelled. Now we know the distance travelled is 1.35 kilometers. We can times that by 1,000, that will be 1,350. So we can say that 1,350, we know that's the area under the graph, and then we can express that in terms of k. So I've split it into two. So this is a trapezium, and you could use the full trapezium formula, but when you have a right angle trapezium, and especially with like everything labeled on it, we can simply work out the areas individually, like treat it as a compound shape. So we've got the base here, this shape is 40, and we've got the height is k. So it must be this red area is 40k. But we then also need this triangular area. And for that I've got a base of 10, and I've still got height of k. So half base times height is I'm going to be adding it, remember, so it's going to be a half times 10 times k. So that is going to become half of 10 is 5, so it's going to be 5k, add the 40k, it's going to give us 45k. Alright, you could divide through by 45 and figure that one out, but I'm going to do it a little bit the sneakier way. I've already done a division of this basically by 5, except there's now an extra 0 on there. So if I divide through by 5, I'm going to get 9k on the right hand side. You don't normally solve equations like this. You normally would divide through by 45k, but the fact that I don't have a calculator, I'm just doing it what I think it was a more efficient way. So if I do 135 divided by 5, I get my 27. I'm going to get 270 here. And now I see how many 9s go into 27? 3. So it's going to be 30. K is going to be 30. And it's in meters per second. It's already given me that. Now that makes sense because the average speed was 27. So if the average speed is 27, I'm going for K for a lot of it, and then below it, it makes sense that K is a little bit larger, but you can see there's only a short period where we're decelerating. So yeah, that makes sense, 30. Calculate the gradient of the graph in the final 10 seconds of the journey. So now I'm just focusing on this triangle. I've just worked out what K is. So the gradient is rise divided by run. And I'm going down by minus 30 is my rise because I'm going down 30. And then my run is going to be 10. So my gradient is going to be minus 30 divided by 10. And that's going to be minus 3. Describe what this gradient represents. Well, it's a gradient of -3. Okay, what have we done here? We've done rise divided by run, which is speed over time. Just like average speed is distance over time, or if you're going at constant speed, actually speed is distance over time always. If I have a constant gradient and I'm doing speed divided by time, that becomes the acceleration. So it describes the acceleration. Now, the answers, the mark scheme allows acceleration, but it actually wants you to write deceleration. But I don't like that because I would say it's an acceleration of -3 meters per second squared. I would say it's a deceleration of 3. So if you're saying a deceleration, that measures how fast you are slowing down. But because we've got the negative here, I think it should be an acceleration. It's a minor point. You get away with either. But later on, like in A-level and stuff, you would always say that it was a deceleration of 3 meters per second squared and acceleration of -3 meters per second squared. In any case, I think that's enough. Like, we just need to make sure we're referring to what speed over time gives us, and they do expect the unit to be put in as well. It's meters per second and how fast that changes per second.